Since it's 4 o'clock, I was just starting. So we started with, in January, applying research in STEM classrooms. Hi, I saw Katie just logged in up there. STEM education for a sustainable world came next, where we looked at how we could apply what we'd learned in the first session about STEM education to teaching about sustainability, followed by computational thinking and coding in the classroom to see how that extends across the STEM subjects. And finally, for me, the last one, energy, the elephant in the room, is my sort of like hobby horse, if you like, because energy for me is the one thing that we really need to think about all the time. It's behind almost everything we do. All the sustainable goals that we want to reach all require energy, except a very few, in some form. So energy is always there, but we just never think about it. But not only that, of course, energy itself is a totally abstract concept. It doesn't exist in any form, although if you go back 200 years, energy was thought to be some sort of fluid which flowed from hot things to cold things, phlogiston. But anyway, let's begin with energy, the elephant in the room, and take a look at our program for tonight. We have Franklin, who's going to show us something about an energy meter, version 2. Hans-Martin Hilbig is going to talk about battery life, and going to look at how we can look at the power consumption of electronic devices, keep it to a minimum. Markku Parkkonen from Finland will talk about student worksheets in physics and chemistry. Katie Baars from the Netherlands will extend what Hans-Martin Hilbig will have been talking about by looking at easy experiments with solar cells and penlight batteries. And finally, Harold Herzig from Minova will talk about the challenges which face the energy industry today. So without any further ado, Stefan, if you could hand the ball to Franklin. Franklin, you now have the ball. So Franklin Neyt with Energy Meter version 2, it's over to you.
And now you can see my PowerPoint.
We can indeed, yes, perfect.
Yes, so the first energy meter only measured the voltage, and now we have energy meter 2.0, who actually measured the energy, and that's what we all have at our home, the energy consumption meter. The energy consumption meter measures the power we use in our home so that the electric company can send us a bill. And that bill, if we use a lot of energy, is a very high expensive, because in the news was the prices of gas and electricity are increasing day by day. So here you see that meter that you can have at home. Old one that is mechanically, or the new one that's digital. And the digital one can measure it constantly. So the electricity divider can measure your use every moment of the day for when he wants. And despite by the old one, you need to give him the actual reading once in a year. What can we do with that information? We can say we need to be efficient with the energy we use, so we can lower our needs, so we can reduce the costs we need to pay and save the planet by doing that. We can also make our own electricity, and we can optimize the electricity we produce. So that's the 3 things we can do to have less energy and less cost and a better environment. So what is measured? That's a small joke. It's what that's being measured, because it's the inventor James Watt that has the theories that apply on these meters. And the meter registered our power consumption in watt. The electric symbol is P. And that's amount of energy multiplied by the time that deliver us watt hour, and in per thousand in kilowatt hour. And in Belgium, we pay between 5 and 15 cents for 1 euro cent for 1 kilowatt hour. So if we use a heating element from 1000 watt during 1 hour, we pay between 5 and 15 cents for doing that. So if we do that a year, we are going to pay a lot. What are the appliances that use that electricity? That are lights, that are the engines, our vacuum cleaner, our electric gate, our electric car, and the heating elements in our home, the ovens, the microwaves. So on these three things, we can work to reduce the energy needs. And the simplest thing is to work on the lights. Lights, in our home, we don't have that light much, but in our schools, we have much of these lights. That's the old TL technology. And in a classroom, you have easy 20 of these old tubes, and these use 36 watts for one tube. And the new technology is the LED. That's the same package, but the new technology. And such a LED tube uses 8 watts for one tube. So if all schools replace the TL tubes with the LED tubes, they decrease the amount of energy they use with 4.5 times, and having the same amount of energy approximately. And with our TI innovator technology, we also have LEDs. We have the RGB array. And that's a little bit the same that inside a TL lamp, it are an array of LEDs. And the questions we can send to the students, it's what's the power consumption of these 16 LEDs? Different with the color, with the white color or the yellow coloring, has that influence. What's the influence of dimming the light? So if we send less energy to the lights, we get less light. But sometimes it's okay to have less lights because you want to have a PowerPoint presentation, and then is light factor that is a little bit disturbing. And the question we also can ask, can we calculate the cost of our light usage in our classroom? And calculating the power consumption is very easy. Hans Martin is going to explain that also later on. It's the power is the voltage multiplied by the current. And the RGB array has a voltage of 5 volts. And our RGB array, our TI Innovator Hub RGB array, can measure its current. And it's quite simple. You have the program in BASIC. You need to send a request, send read RGB and get I. Then you have the measurement in milliamps. Or in Python, current is light spent measurements, and then you also have the measurement in milliamps. And if we do that, we have an example. When all the lights are almost fully on, RG and B at 250, the maximum amount is 255, we measure a current of 38 milliamps. If we have a little bit less light, so it's darker in the room, RGB at 120, we have 17.2 milliamps. And when we have a yellow light, that means that blue is off, we have 28.6 milliamps. And if you calculated that by multiplying it with 5 volts, we have 190 milliwatts for a full light RGB array. And that's normally that's 190 milliwatts because our RGB arrays give less light than a TL tube, because a TL tube has the power of 220 volts, and we have RGB LEDs with 5 volts. So 5 volts give much less power than 22 volts. And you can let the students play with different variations of that, and they get different amounts of current and amounts of energy, and you can ask them to have conclusions. And one of these conclusions is that if you go to yellow light, you have less current, so less power. So the lights that are giving yellow lights have less power consumptions than white light. If you dim the lights, you have also less current because you decrease the amount of red, green, and blue. So the LEDs need to have less energy, so they are giving less amount of light, so less power. And then you can ask them to calculate the cost of that. And it's quite simply. The power is your measurement multiplied with 5 volts. It's in milliwatt. And you need to know the kilowatt hour. So you need to divide how long is our lights on. So you multiply that with the time that it's on. In the program, I use time is time plus wait time. So I set the program in a loop, and I add the loop time, the wait time in the loop by the time. So I can multiply it. And 10 cents for 1 kilowatt is 0.00001 cents for 1 milliwatt hour. So if you multiply with the time and with that price, you get the price it costs for letting our RGB array on for a while. For the measurements, we are going to set that 1 second actually is 1 hour. So it's a simulation of a real-time application, but it's going much faster because you said 1 second is 1 hour. If you've done that, then you can see that reducing the power is an element you can use. And what can you do? You can reduce the lights in your home, make it darker, but you can also reduce the engines. If you have an electric car, you can use less throttle, so there's going to less energy to the engine. It's less powerful, but lesser use of the battery. Also, heating elements. If you use a heating element at a lower degree, it needs less current, so it needs less power. So all small things have a little influence on the power usage and your energy meter that's in your home. And then you can give the students a couple of tasks to reduce that cost. By examples, use the light sensor that's in the hub of an external light sensor to let the students control the light of the RGB array and function of the light that is measured with the light sensor. Because when you it's a sunny day and you are open the curtains, like the curtains behind me, then you have natural sunlight in the room, and natural sunlight is of course much better than sunlight of the light bulbs. So you can ask students to make a thing that reduces the amount of the light bulb light in a way that correlates with the light that is entering the room by the sun. Also, you can let the lights off when there is enough sunlight in the room, because when it's light enough in the room, you can say it now becomes dark automatically. And the last experiment is something what's present in most rooms that are built today. That is only light when there is a presence in the room, when a person is present. That are at many bathrooms these days. When you enter a bathroom, the lights go automatically on because there is a person in the room. And when you are there not anymore, after a while, the light go automatically off. So you never have in a room the light on when there is no person for a period of time. And that's in real life the work of a PIR sensor. And you can also use a PIR sensor, that's a digital sensor, as an external input of the innovator hub. So that was the first part, the part that used the energy that is entering your home. The second part is you can produce your own energy. And that's something what Katie is going to explain further. That are experiments with solar cells, small windmills, and a fan, or a generator, by example, an old bicycle generator. Because the old bicycles have a dynamo that harvest the motion of the tire and then set that in voltage, and that voltage goes to the lights. And nowadays everybody wants to bike freely, so don't have that generator anymore, and the bicycle lamps are with the batteries. And this is a circuit that is very easy. At the left, you have energy production. In this circuit, it's a solar cell that's harvesting energy. That's harvesting is not the correct word. It's a translation of light energy to electric energy. And that is dependent on the amount of light that is on the solar cell. And this energy you measured with a voltmeter. And we have a voltmeter in our innovator hub. We have 3 voltmeters in the hub. At the middle part is a special electric component. It's a diode. And a diode is used to make sure that the energy can flow from the solar cell to the battery and not from the battery to the solar cell. So there's only one way that there is a flow of energy possible. And you have a second voltmeter after the diode, and that's the voltmeter that measures the voltage of the battery. Important is that you use a battery that is able to receive energy. So a normal alkaline battery of 1.5 volts is not the good battery. It needs to be a rechargeable battery of 1.2 volts. And the key is that with the innovator hub, you can measure the left voltage and you can measure the right voltage. And if the left voltage is 0.6 volt greater than the right voltage, we know that the diode is letting current through, so we know that the battery is charging. If the left voltage is not 0.6 volt higher than the right voltage, then there can't be current from left to right, so the battery is not charging at that moment. That's happening when there is no sun on the solar panels, or if you use a small windmill, when the windmill is standing still, the battery can be charged. And we can write a program, the students can write a program that is showing on the display charging or not charging. I've mentioned here 0.6 volts because 0.6 volts is the tension, the voltage of a normal diode. In this situation, you use another diode, and that's the diode that Hans Martin has in his presentation, and diode only use 0.2 voltage. It's a better diode than a standard normal diode. And how you can measure voltage is quite easy. It's because we have in the Innovator Hub analog in pins. And that's our 3 pins we can use. That's BB5, that's BB6, and that's BB7. That are the only 3 pins that can measure the voltage. And there is a rule, the voltage must be lesser than 3.3 volts, because that's the voltage that the hub used as a reference voltage. We also need to watch out for the polarity. The highest voltage needs to be on the BB5 pin, and the low clamp needs to be at the ground. So the current needs to go to the BB5 pin and not to the ground pin. So that's the program there in basic language, very simple. Connect analog in, read analog in, and we get a value. That value is not directly the voltage we measure, it's the result of the analog to digital converter that's inside the Innovator Hub. If we want to do that in Python, it's much simpler than in BASIC. In Python, we need to say input is analog in, and then input .measure, and he measures the result of the analog to digital converter. And then we need to make that result to voltage. And that's a little bit electronic circuits. ADC converter is a way to set analog voltage to a digital number. And the converter that is inside the hub has 14 bits. That means that the voltage can be converted to a digital value between 0 and 2 to the power of 14. So that means that there is in total 16,384 values. With use of a minimal value of 0, we have one less than 16,384 over as the maximum value. So we had getting a voltage converted to a number between 0 and 16,383. And if we want to convert that number we measured to voltage, we need to have the number we measure. We divide it by 16,383, and we multiply it with 3.3 voltage, what's our reference, and then we have a voltage as a result. So you see here in the Python program that you are getting at a Python shell that there is printed meting zoveel volt. And he does that 10 times to see any difference. You can use many things. You can use a wire directly to the BB5 pin or the BB6 or 7, or you can use a device like a resistor, a potentiometer to measure a certain amount of voltage, or a solar cell. Important by that is that we don't exceed the voltage of 3.3 volt, because if we are having a car battery, by example, of 12 volts, and we want to measure how many power voltage there is at the car battery, and we connect these 12 volts to the Innovator Hub, then the Innovator Hub can be damaged, because there's a great amount of energy in the system, and the system can't handle that amount of energy. So we need to be very how do I say that? Be careful what we do.
So cautious, maybe?
Cautious, and that's the word I was searching. So very cautious what we do. When you let students this doing in a lab environment, you can better measure the voltage first with a voltmeter, and then give the permission to attach the volt to the hub. It is possible to measure voltage with greater than 3.3 volt. That we can do with a simple circuit, and that's in this here slide, the tension that is divided by two resistors. So this voltage divider. So if we have an input of 12 volts and we took a resistance R1, by example 750 ohm, and R2 250 ohm, that's together 1000 ohm, then we get on the BB5 pin 250 divided by 1000 is 1/4 multiplied by 12. So 12 divided by 4 is 3 volts. So if we do that, we get our car battery from 12 volt is a voltage of 3 volts on the BB5 pin. So the resistance number 1 gets the energy that is too much for the innovator hub, and the innovator hub gets only the tension of 5 volts that's over 3 volts that's over R2. And that we can also use by the solar panels or the wind turbines or the battery or the dynamo of the bicycle to make sure that the voltage is not too great for the innovator hub. The only thing you need to do when you use this circuit is your factor that's dividing, multiplying with the results you have in the earlier measurements to know the real voltage. So the innovator hub says in the example of the car battery, you have 3 volts, but you know I have used a divider by 4. I need to multiply with 4 to get the real answer because you used this circuit. And that's quite easy to do that and very fun in the classroom. And the last part is we have harvested energy, we have consumed less energy, how we can harvest more energy. Because we are all have solar panels at our houses, but when the sun is at another angle at our solar panels, the amount of energy a solar panel harvests is more or less in comparison with how the angle of the sun is. So in summer you can have a high output of your solar panels because the sun is at a high angle, and in winter you can have less energy because the sun is in a low angle and you have a little shade of a building, etc., etc. So we can make something that is in theory. It's also in some practical. I have seen it in the neighborhoods here. Is there a home that have solar panels on a turning table, and the solar panels are turning towards where the sun is, so following the sun. And this we can simulate that turning table by doing the following. We have at an angle, the green one is our solar panel. At an angle, we have a meter that measures the light. So a light meter on the left at an angle and a light meter at the right at an angle. And we have 3 situations. If the sun is at point 2, then the left meter and the right meter are getting the same amount of light directly into the sensor. And that means that the sun is straight on the solar panels. But when the light is on the left sensor, the sun is straight hitting that sensor, but sideways hitting the second sensor. So when the sun is at position 1, the left sensor is having a higher reading than the right sensor. And when the sun is at position 3, we have the opposite. Then the right sensor has more light into it than the left sensor. And we can determine if the sun is at 1, the whole turntable needs to turn clockwise. And if the sun is at 3, the whole turntable needs to be turned counterclockwise. So we can program something like that says at the display of the calculator, turn to the left or turn to the right because the sun is left or right, clockwise or counterclockwise. This program is in basic still. Read light level, very simple. And you have these 3 questions. And here I do something special. I say B1 is less than B2 min 1000 and B1 is greater than B2 plus 1000, because if you're having a turntable, your solar panels are using a motor to turn, and you don't want that the motor is on all the time and turn to the left and turn to the right and etc., because then you use energy to harvest more energy. And if you use more energy to turn your solar panels, then that you're one with doing that, you are not optimizing the system. So I use minus 1000 and plus 1000 to create a special effect that if the sun is turning, that the difference needs to be great enough to actuate the motor and to turn in the direction of the sun. You see that in this representation, normally you should turn counterclockwise and clockwise almost every time. And in the second, he turns clockwise, he's not moving, and the sun is going further and further and further, still not moving, and then the engine is starting to turn clockwise. And in the other direction the same, turning clockwise, then time it's not moving, and counterclockwise. So if there are small difference, that's the zone here, then the motor is still. And that's a method to let your solar panels harvest more energy. And that was it all. And I see that I timed it very neat.
Perfect timing, Franklin. Yes. Thank you very much. That was very, very interesting. For me, it was particularly interesting because you started off with a topic with tonight's program, which highlights for me one of the principal reasons why energy is the elephant in the room. And that is because our school curricula tend to focus on the energy which children and their families use in the house, the household use of electricity. And time again, they never really understand that actually their demand, their electricity demand is much higher. So you used a unit, the kilowatt hour, as a unit of energy there, or it could be the kilowatt hour per day, which is a unit of power. And the kilowatt hour per day is about 10, I think, roughly, for families using electrical energy, and possibly 10 for their gas energy for heating. But in fact, so that would give 20, but in fact, their average needs are something like 150 kilowatt hours per day, because of course, all the other things they have, it's not just their car, but their clothes and all the devices and things which are made inside the house. Even the house itself is manufactured from bricks and stuff like that, all of which requires an energy input. But there is what I have a question here, or not a question, it's a comment from John Hanna, who made an interesting comment about the use of 4.5 times less, which is quite interesting. So you right at the beginning, you had the fluorescent tubes, I think, and the LED tubes.
Yeah.
So would you, is it, you use 4.5 times less because you're translating from Flemish into English there. 4.5 times less energy, because he would want to say, I think the old one uses 4.5 times more energy than the new one, rather than the new one using 4.5 times less than the old one. So he just wanted to put it the other way around.
It's the same.
It's the same for me, but for him it's a pet. He calls it a pet peeve. So it's for him it's a.
I want
thing.
to emphasize that we need to consume less.
Yes.
So that's why I say it's 4.5 times less. And the reason that schools are having that old TL lamps is because they say they work. And we need to invest a lot of money into new ones, and they do the same.
Mm-hmm.
And they don't think that they can win euros or dollars if they invest in more expensive lights, because they have workers to go on a stair to change that. The light bulb is more expensive because an old one is cheap and a new one is expensive, but the new one is in later time more better because you reduce your energy cost, but the cost to buy a light bulb is higher than buy an old technology. So
yeah, but I think so. You and I are sort of technicians at the other side. So John Hanna is a mathematician, I believe. So he's a purist, you see. He's thinking, 4.5 times less. Well, actually, you mean 1 over 4.5 times the old.
Yeah.
So he's just being pedantic about the use of the word times, I think, in that expression. But we all understood exactly what was meant. And
that's the meaning.
Really interesting. Yeah, that's the main thing. I can't see any other questions down there. Christine, did you see anything?
No, I didn't see anything, but if you allow me a little comment on this.
Go ahead.
Absolutely.
People probably know me already. I don't want to be a killjoy, but my comment to this story is that the thing you can measure in your lab and all that stuff, and telling that TL lamps are consuming more energy than others, that's true. But to me, as we have the topic of the energy as an elephant in the room, we also have to look at the whole picture, and that would include how much material, how much energy, how much soil, how much water the LED lamps were consuming to be produced. And this would be the whole story you should add to your calculations. And then I bet that probably the school's saying, well, it's too costly. Yeah, that's an argument, but you can also say, well, as long as the old lamps are functioning, we save planet resources and don't waste them in just throwing away functioning lamps just because the other ones are using up less energy when they are running, but I bet they were consuming much more energy when they were built.
Yeah, that's true.
Yeah.
We will come to this topic, I guess, further on too.
But Franklin, can I respond on behalf of you?
Yeah, that's correct. Okay.
Because what Franklin, of course, has presented is the meter rather than the new lamp. The idea of using an energy meter. For me, I had one of these smart meters once in my house, and it did prompt me to use less energy. So whenever I noticed that the meter was high, I would think to myself, hang on, what have I left switched on somewhere in the house? And I'd be going around the house switching things off. And it did prompt me to use a great deal less energy than I would have done had I not had an energy meter going. So you mentioned that right at the beginning, Franklin, I believe. Yes. The psychological effect of using an energy meter.
And the comparison between the TL and the LED lamp was a clothes hanger to the story of the RGB
Yes.
array.
Yes, yeah. So that was very interesting. Anything else there? Can't see anything. No. Okay.